So, good morning, everyone. I am here to present on the topic how finite automata is powering search technology, that is, the applications of finite automata in search engines. Myself, Ishayu Roy, and my registration number is 23BCE1148. So, let's proceed with the presentation without wasting any time. So, before diving into the main topic, the most important thing is to understand what exactly is a finite automata. A finite automata. A finite automata is an abstract machine which is used to recognize pattern in input sequences, forming the basis for understanding of regular languages in computer science. They consist of states, transitions, input symbols, processing each symbol step by step. If the machine ends in an accepting state after processing the input is accepted, otherwise it is rejected. A finite automata can be defined as a five-state tuple: capital Q, sigma, small q, f, and delta, where q is the finite set of states, sigma is the set of input symbols, small q is the initial state, f is the set of final states, and delta is the transition function. So basically, a finite automata is a machine which will recognize a string pattern. So let's say I have to process my registration number. So my registration number is 23BCE1148. Year 23 stands for the year in which I was admitted to VIT. BCE is my course or branch, that is Computer Science Engineering core, and 1148 is like a unique identification number. So here the there can be like 23BCE1148. We can have like each state for that's two numbers followed by three alphabets followed by four numbers. So that's like 4 plus 2 plus 3, that's like 9 states. So there will be total 10 states in the finite automata, say S0, S1, S2, S3, and so on to S9, followed by coming to the alphabet set elements. So the alphabet set elements will definitely be the digits 0 to 9 and the alphabets, let's say A to Z. Initial state will be S0, and the final state element would be the final state, which is S9, let's say. And transition function is nothing but it denotes the transition from one state to another. So like delta of S0, comma, something in between 0 to 9, which is the first digit of your registration number. Mainly, it will obviously be 2 because you are not admitted into VIT before the 2000s, let's say. So basically it is 2. So you reduce it to 2 as the transition. So delta of S0, comma 2 will take you to S1 and so on. Coming to the next slide, this is basically a finite automata. So here A is the initial state, B and C are the non-finite state elements. That is, if the string is ending here, they are not accepted. And D and E are the final state elements. So talking about the ACE branch, it's basically if the first symbol is 0, you move on to C, and then the next symbol is 1, you move on to E. So the string 0, 1 is the only one string which is accepted by the ACE branch. Now coming to the ABD branch. If the first input is 1, you move on to B, and then if you encounter any number of B's, you just stay on B itself. That is, it's a self transition. And then on encountering a 0, you move on to D. So basically, which is the final state element, so the string gets accepted. So basically, the finite automata recognizes the string 0, 1, or else the string which has at least one binary digit 1 and ends with 1, 0. So that's all about finite automata in general. Now, coming to the point which I had mentioned before, that finite automatas are used for pattern matching in regular languages. So, in general, regular language is a language which has no kind of dependency on the input symbols. Like each input symbol is dependent of each other. So now, coming to the part that about the algebraic representation of regular languages, how is it done? So these are done through a concept known as regular expressions. So now regular expressions have the following rules. That is, any terminal symbol is a regular expression. The union of two regular expressions will also be a regular expression. The concatenation is a regular expression. The iteration or the closure is also a regular expression. And basically, it is obtained by recursively applying the above rules once or several times. Coming to the iteration or closure representation in TOC, there are two types, the clean closure and the positive closure. The primary difference between them is that a clean closure accepts a null string while a positive closure doesn't. So positive closure is representing all set of all strings except null or epsilon strings, and one which accepts the null or epsilon strings is the clean closure. So a positive closure would give you the strings A, triple A, quadruple A, etc., and so on. While a clean closure will gives you a null string A, double A, triple A, and so on. That's all about regular expressions. Now moving on to understanding search engines. So what exactly is a search engine? A search engine is something which is very common to our life. Anything which we want to know, maybe um, the birthday of our favorite cricketer, the live cricket score, or maybe some research article for our DAs, etc. We just open Google and type. So what is Google? It is a search engine. Let's look on to the formal definition. So a search engine is a program that searches and identifies items in a database which correspond to keywords or characters specified by the user, especially for finding particular sites or content on the World Wide Web. So some common search engines are Google, Bing, Yahoo. Here are a few in the image below. You can have a look. Moving on to how does search engines work? Search engines operate via three core functions: crawling, indexing, and ranking. And these operations take place in a sequential manner as listed below. So, crawling involves coding the internet for content and meticulously examining the code and content of each URL which you encounter. Indexing follows this, where the content discovered during the crawling phase is stored and organized. Once a page is indexed, it becomes eligible to appear to view relevant queries. Ranking. Ranking is the process of presenting the most fitting pieces of content to answer a searcher's query. This entails arranging results from most to least relevant. Following is a diagram which represents how Google works on getting its data. For example, you are publishing an article, let's say about military diplomacy in your website. The Google bots or spiders will crawl and review your pages. So it's the Google database gets aware that okay, there is a site which has an article or report about military diplomacy, and then your page is indexed. And then this page is further analyzed, and based on the Google ranking criteria, it is given a certain rank on how much similar it is to what Google wants it to be. And then when a user enters, let's say military diplomacy, based on the Google ranking, your article on your site would show up in his search results. So this is how Google or any other search engine for that matter works. Now having basic idea about how search engines are working, it's time that we understand that where finite automatas are being embedded in the search engines. So the first application of finite automata is string matching. What is exactly string matching? It's nothing but comparing a string and deciding whether it follows a specific pattern or not. So, like, suppose we have a database of articles of military diplomacy and the user enters military diplomacy. So, this user text is compared to the military diplomacy in your database, and only if there is a complete match do you get the results. So, this can be done using a finite automata for parsing the text and matching it. So let's say you have a predefined pattern in a database that all the strings which are present in a database can contain only two consecutive A's, but not two consecutive B's. So here is a finite automata for the same. So if you want to have like a quick review of the automata, we can see it. The starting state is 0, and the final state elements are 2 and 4. So on encountering an A, you move on to state 1, and then if you encounter an A further, you move on to state A. Now you have a double A. So you are standing at a final state element at present. Further, if you receive an A, you can just go on a self-transition loop and your string will get accepted. But from state 2, if you receive a B, there is a probability that you get two consecutive Bs. So you move on to state 4, which is by itself is also a final state element. And wait. If you receive a string symbol A, you move back to state 2 and your string is again getting accepted in a loop. But if you receive an input symbol B, it means that you have encountered two consecutive Bs. And from this, no matter whatever input comes, the string can never get accepted. So a 4 with B takes you to a state 5, which has a self transition with A and B, including anything after this will not let your string to get accepted. On the other hand, if the starting symbol was a B, so you are moving to state 3. And after 3, if you are encountering an A, you can move to state 1, because then there is a possibility of finding another A which fulfills your condition of two continuous A's. Similarly, if we see, and after getting a single A from the starting point 0 and moving to 1, if we get a B, we can just come back to 3 because it will check for the double B next. We can see that. So now from 3, if you don't get an A, you get a B. And from that B, you move on to state 5, and basically you are done with two consecutive Bs. So your string can never get accepted. And again, in state 5, A or B, whatever comes next, cannot lead a string to get accepted. So it stays in state 5 itself. So this matching algorithm will take some time of like big O of MQ plus N, where big O of MQ is to build the state table and big O of N is to simulate it on the input file. So you can see the transition table here. The states and transitions are given, that the present state and then the next state based on the transition A or B. So like 0 with A gives you 1, 0 with B gives you 3, and so on. On the other side is a table where we have an input string BABA, BAA, BAAA, BBAAB. So clearly this has the string B, so it can never get accepted. So the table below shows us the transition for each input symbol when it's recorded, and we can see that finally we end on state 5, which is not an accepting or final state. So the finite automata will reject the string. That's as simple as it is. Okay. Now coming to the efficiency analysis. So this type of algorithm by itself has some advantages, definitely. These advantages are like the determinism and simplicity. It's very easy to understand a finite automata than to understand maybe some piece of Python or C code which is doing the same purpose. Efficient pre-processing. The construction of the transition table is pretty easy because it's based on the input symbols and states. Then it allows for parallelism, and then it also helps in handling multiple patterns, like you can club in patterns as in concatenations or unions, etc. However, there are certain disadvantages as well. The first one being a finite automata has a very limited small memory. The inability to handle complex patterns, both one due to lack of the memory, and the second one also being that if the pattern is very complex, the regular expression is also complex for it, which increases the number of states and makes it difficult for construction and understanding. The third point also builds up on the same, which is the complexity of building the automata. So in general, we can sum it up as since a finite automata has a very small amount of memory, it cannot process very large strings having complex patterns, because even if it can, the automata might be of 500 states, 1000 states automata, which is very difficult to construct and understand. So with this, we can also focus on some other algorithms which can be used for string matching, and you can have a look on it by the net for better understanding of them. The Knuth-Maris-Pott algorithm, that is the KMP algorithm, the naive algorithm, the Aho-Korasik algorithm, the fuzzy string search, and many more. Next up, we have auto-completion using the finite automata. So coming up to what is auto-completion, we see it every day. Open WhatsApp, open the net, and you are typing. Suppose you want to type beautiful, type BEA, and it shows up in the option beautiful. This is, and you click on it and it gets filled up. This is auto-completion. So now let's try to understand that how finite automatas can be used to come up with such autocomplete sequences. So simple extension to the DFA, that is the deterministic finite automata definition, can greatly expand their power to in the meantime it also preserves the ability to encapsulate ideas and processes. So one such extension is the finite state transducer, an FST, which adds an output capability to the DFA. So the figure in the next slide, which we will discuss shortly, illustrates the use of a mealy machine, which is also an FST, to index strings in the ordered set mop, moth, pop, star, stop, and top to produce the numbers corresponding to the alphabetical order within the set. So you can have a look at the FST for text lookups in this case. So let us consider the word stop. So um, it is the fifth element, index 4 of the set. So beginning with the start state, we follow the S arc. Now the S arc is associated with an output of 3. Then we move on to T, which has no output, and then we take the O arc, which is an output of 1. So currently the sum output stands at 4. And then we follow the P arc, which again has no output, and we reach the end of the word with the output sum being 4, which is also the index of the word stop. So now coming to this FST approach or the algorithm, what is the advantage? The primary advantage is that common prefixes and suffixes of the stored terms are shared, greatly reducing the memory footprint required for text lookups. Now, an example of such system, it is the Apache Lucene project, which used an FST to dramatically decrease the memory footprint for the autocomplete search term feature. Coming up next, we have spell check using finite automata. So, like you must have seen that, for example, instead of typing, let's say beautiful, you type something else, maybe some minute error in the spelling, like BAEUTIFUL. So you get a suggestion saying, "Did you mean beautiful?" The correct spelling. So how does this work? So basically, there is an ability of the search engines to analyze the words which are most closest to it and have a meaning in the stored database or dictionary. So this process is based on the calculation of something which is known as the Levenstein distance. So what is the Levenstein distance? It is basically the minimum number of single character edits, which is insertions, deletions, and substitutions required to change one word into the other. For example, to change star to stop, we need to substitute A with O and R with P. So it will have a Levenstein distance of. So what we can do from the Levenstein distance is we can generate something which is known as a Levenstein automata. And you can see from the definition given in the slide, Levenstein automata for a string W and a number N is an automata which can recognize the set of all strings whose Levenstein distance from W is at most N. That is a formal string in the that is a formal string X in the language recognized by the Levenstein automata is if can be recognized if and only if X can be transformed into W by at most N single character insertions, deletions, or substitutions. So in next slide, this is a non-finite Levenstein automata for the word salad. So the states have a notation I hash X, where I stands for the characters which have been read in the pattern, and X is the errors which have been recorded. The horizontal transitions represent identities, vertical transition represents insertions, and the two types of diagonal transitions, sigma represents substitutions, and epsilon represents deletions, respectively. This topic has not been touched upon in detail because further research work is going on this and requires further edits and improvement. Next up, we have URL matching with finite automata. Since we have already discussed something known as the string matching pattern, we can also in a similar way match URL. It's not necessary that always a user will type some word. They can also want to visit a particular site and type the URL for it. So we also need to have a pattern for checking the URLs. So it's nothing but URLs can also be converted into simple regular expressions. And then these regular expressions can be validated by a finite automata. For example, here is a finite automata which validates the word nice. Assume it's a URL. So you start, and then if you get N, you go to a state N found. If you get I, you go to a state I found. C to C found, and then E you represent success. And for E you represent the success. For any error in any state, you go to an error state and display error, which in this case is basically an error 404, that page not found. Coming to the summary of this presentation. Finite automatas are foundational in search engines for text processing, searching, auto completion, error detection, etc. Their use is essential in delivering fast and accurate results, and with continuous innovations, they can contribute even more to enhancing the search engine performance. Future scope. So, what we have seen is currently, while exploring the finite automata, that there are some limitations to its working. It is not being able to process large data sets or complex patterns because of the lack of memory. So in future, what can be done is that you can combine these finite automatas with AI/ML models to allow for more sophisticated pattern recognition and query understanding. Then some other technologies could also improve finite automata's ability to handle complex queries, increasing their utility in processing variables. Then advances in the finite automata technology could allow real-time updating of index content, enabling more immediate and relevant search results. So we hope that there are more researches being continued in this field, which can help to develop more powerful finite automatas, which can be used for the search engine optimization. For completing this PPT, I have referred from various research papers, articles, websites, even YouTube videos. So here are a list of some websites or YouTube videos which I have referred as a reference. I would like to thank all for their valuable content. And that's all from my side. Thank you so much for listening to me. And as you can see, this is just a finite automata which accepts the word thanks. That's all. Hope to meet you. Thank you. Have a great day.